Dear students, today we are talking in continuation to the electromagnetic induction theory. So now we must talk about, or we can understand, Faraday's laws of electromagnetic induction. Michael Faraday has initiated two laws to explain electromagnetic induction in detail. They are called as the Faraday's laws of electromagnetic induction. First law of Faraday states that whenever a conductor cuts or otherwise a coil cuts the magnetic field, an EMF is induced in the conductor or coil, or otherwise whenever magnetic field links with the conductor, then also an EMF will be induced in the coil. So both the terms will be used practically. In future, when we will be talking about the machineries, electrical machines, there once again I will tell you about the first law. As per the second law, see, the first law, whenever conductor is cutting the magnetic field and EMF is inducing, is giving an idea that whenever the magnetic field and the conductor they are linking, EMF will be inducing. But how much EMF is induced is not explained by the first law. That is being explained by the second law. Second law states that EMF induced in any coil or the conductor will be equal to the rate of change of flux linkages, and is expressed as E is equal to N into d phi by dt. N is the number of turns in the coil. If the conductor is bent in the form of the spring, that will be called as the coil. D phi is the change in magnetic flux. dt is the time required to link the link of the magnetic flux, which is denoted by the negative sign. Why? Because the induced EMF will be always represented with the negative sign according to Lenz's law. One more scientist who discovered about the direction of the induced EMF. Lenz's law. Lenz's law states that the electromagnetically induced EMF produces a very cause. It will mean it opposes the very cause which produces by it. The meaning is, the induced EMF, if it has reached to the saturated period or stable, at that time further magnetic flux is not required, it will oppose. It means it maintains the stability of the voltage. So Lenz's law will be practically very useful. According to that one only, the direction of the back EMF induced in the machinery will be known, and the electromagnetically induced EMF in the stationary machine like transformer, choke, buzzer, etc. will be also known. So practically it is usable. So on account of the Faraday's laws, there will be two types of induced EMF in general. One is dynamically induced EMF. The other one is statically induced EMF. First is dynamically induced EMF. The second one is statically induced EMF. Further, this statically induced EMF will be classified into two groups. One is the self-induced EMF. The other one is mutually induced EMF. First one is self-induced EMF. Another is mutually induced EMF. Now this is practically the example for choke. Choke operation will be on the basis of self-induced EMF. The practical example of this mutually induced EMF is transformer. When these machineries will be discussed in detail, once again the example you can understand. So now we can talk one by one. What is the dynamically induced EMF? What about the statically induced EMF? And how they are classified as self-induced EMF? What does it mean? And what about the mutually induced EMF? How it is to be explained, why it is called as a mutually induced EMF? We will discuss. So first is dynamically induced EMF. So for dynamically induced EMF, you consider these three figures. These are the magnetic poles and here the magnetic lines of force will be flying from one pole to another. So normally north pole will be sending and south pole will be permitting to terminate the magnetic lines of force in it. So assuming that here a conductor AB is placed in the magnetic field and its magnitude will be given by E is equal to B L V sin theta. Now you see, the conductor AB is not cutting any magnetic field. It is parallel with the magnetic lines of force, and the diameter of the conductor which is linking with the magnetic lines of force is negligible. That's why here the induced EMF will be 0. Then in the second case, suppose that the conductor AB is placed, as it to be like this vertically 90 degrees to the magnetic field. Everything is fine. That is, E will be equal to B and V sin theta will be equal to maximum. Why? Because everything is maximum. The maximum flux density it will be acquiring, and length of the conductor which is making the contact with the magnetic lines of force is also very high, and velocity or the speed of the motion of the conductor is also very high, and the theta which is the angle between the magnetic field and the conductor is also 90 degrees. Sin 90 is 1. Therefore the induced EMF will be very, very high. That is the maximum. So coming to the conclusion, in the third case, the induced EMF, dynamically induced EMF will be lying in between 0 to 90 degree anywhere. If it is made like this, if it is a 45 degree conductor AB if it is making, then once again E will be equal to B and V sin theta if it is taken. Now the voltage induced in the conductor will be depending upon this sin 45 degree, whatever the value you will be getting. So therefore, the magnitude of the induced EMF in the cycle you can have in this way, like this, 0 to, this is 90 degree maximum voltage induced, and here it is 45 degree. 45 degree if it is taken, then 0 to 90 degree the variation in the voltage will be there up to 180 degree, then that to 360 degree, here 270 degree, here 2 also you will be getting. So like that the variation in the voltage will be there. So the definition of the dynamically induced EMF is what? Whenever a conductor touches the magnetic field, an EMF will be induced in the conductor. This is the DC generator principle. On the other hand, whenever the magnetic flux will be linking with the conductor, then also the EMF will be inducing with the conductor. That is the AC generator principle. In first statement, conductor is rotating with respect to the magnetic field. In the second statement, magnetic field is linking with respect to the stationary conductor. In both the cases, the EMF induced in the conductor will be utilized in dynamically induced EMF in machinery. That to dynamic machine, generator, motor, rotating machine, they will be utilizing. Its magnitude is given by E equal to BLV sin theta, and direction will be given by Fleming's right hand rule, where E is the induced EMF and B is flux density in Weber per meter square, or otherwise the Tesla. L is length of conductor, that will be in meter. A is, B is velocity or the speed of conductor in meter per second. Is the magnitude of the dynamically induced EMF, whereas theta is the angle between the conductor and magnetic field. Theta is the angle between conductor and magnetic field in degree or otherwise radii. So this dynamically induced EMF will be utilized in almost all the dynamic machine like DC generator, DC motor, totally with rotating machines. So statically induced EMF we will discuss in the next lesson.